Hi all. Just wait for a few minutes. So good evening, everyone. Um, I think a small change in schedule. I think this is an extra session for this week for myself. My original sessions are on this. Um, so I'll be continuing from where we left off on. Okay, and I would also like to a special example being shown today because the session probably is to give you a bit more insights into what you've learned across all of the lecture videos that you've read. So in that sense, you have come across something called data plane programming. Right? So apart from completing the week 10 syllabus, I'll also be showing you an example of P4 program, how it is run, and what is so special about this data plane programming, and how you can develop your own data plane code. Right? So as usual, we go through the questions first, and we note down some keywords and we solve these questions. All right, so before I go, I'll also give you a brief overview of what happened in the last week, sorry, the last session, which are the questions that we solved and what is left out and what is not solved. So we studied something called DCTC, data center TCP. So there's nothing but TCP that is tailored for the data centers. We also saw why do we need a different type of TCP for the data center. So why do we need a different type of TCP for data center? It's because data centers run on very low time scales. Right? You have requests and responses that are completed in microseconds. But if you see across the internet where TCP performs, it is in the order of milliseconds. So because of these low time scales and the fundamental idea of multiple fan-ins to a particular aggregator, what happens is when all of the worker nodes by chance coordinate and send at the same time, there is a queue buildup, and because of the queue buildup, you are losing packets, which leads to TCP resetting, having its own timeout, and sending the packets again. So this timeout is costly. This timeout is a costly affair. Now, timeout is a very costly affair because of the time scales, right? And by the way, I'm just summarizing what we read so far. I mean, why? What is TCP? Why data center TCP? Probably I'll write down on. Yeah, writing down. Okay, fine. So we saw TCP, and I'll tell you the history behind it once again, and how DCTCP solves what TCP could not solve. And also DCTCP has something called the alpha parameter, which probably is something that you would have understood if you had gone through the videos, but I love to talk about what alpha parameter is. But when I talk about it, I'll talk about it in very simple terms, so that it will help people who are not on this background to understand what it is. Right? And then comes the aspect of computing models, right? So we have from the service, infrastructure as a service, and then there's also software as a service, AAS, and there is also serverless computing. This is a recent paradigm. So what is the difference? And in the last class, I also showed you an application that I developed using the serverless computing model using Amazon's Lambda functions. Um, Probably just to give you an idea of how easy it is to set things up in a serverless computing model. Essentially, the serverless computing model is nothing but a a repository of multiple functions, pretty much any function that you can think of. You just call and you can just run it. That's all. You're not managing anything beneath that. You're not managing the operating system. You're not managing the middleware. You're not managing anything. You just have a requirement. You call the appropriate function, then you get the output. That's it. And then comes the move from the monolithic architecture, which was the old architecture, and we saw why this monolithic architecture um, is not um, the best way to move forward. We looked at an example also as to why this monolithic architecture is not cannot scale well. It it's also intensive in terms of monetary aspects, right? And right, so we saw the pros. And then again about microservices, we'll take a look at week in this class, microservices and what is the should be the microservice, and we'll talk about this with respect to web development, web applications. I don't know if any of you are web developers, but from this perspective, if you look at it, probably it will be easy to understand. And then, right, this is something about network processors. Let's see about that. And then regarding software architectures, how do they uh, compare? Right? Then we have this message delivery semantics of serverless architecture. This is directly from the video, but we'll try and look at this also towards the end. And in-band network telemetry. So I'll probably give you an introduction to this with respect to data planes, right? Where you use P4 and what is the need for this network telemetry, in-band network telemetry, and right. So that will be the. I'll just switch over. Right. we saw what NPTEL was, and then we were heading towards serverless computing, which we'll complete today, and the monolithic and microservices architecture. And we'll also go towards in-band network. Right? So DC-TCP, why TCP is not suitable for data centers? Why it is not suitable for data centers? Just because of the latency issue that I specified. And then, so how does TCP work? This, what is the fundamental thing about TCP? Now, this is just introduction to TCP for people who are not familiar with TCP, so they can appreciate the value of DC-TCP. Essentially, necessity is the mother of invention. So they saw something, saw that the TCP was not performing as expected, so they solved the problem and things improved. Right? Essentially, this retransmission timeout of TCP is a major player in terms of why TCP is not performing well. So the idea of TCP is to ensure that this RTO, retransmission timeout, is never reached. If it is never reached, then it never happens. So even before a packet loss happens, the sender is informed to reduce the rate of sending. When sender is informed to reduce the rate of sending, then automatically you scale down the sending process and not overwhelm the queues at the switch buffer, which would probably lead to a reduction in the stress um, and uh, and the queues will be emptied and you won't lose any packet. So packet loss is very costly because of the timeout. The system waits for a few milliseconds or seconds, and that wait is costly. You cannot afford that in data center environments. Right. So how this exactly happens is you have this concept called congestion window in TCP. So when the congestion window in normal case, in normal case, congestion window is cut into half on every packet loss. But now, even before a packet loss happens, when an indication occurs that the queues are getting filled, then the TCP's congestion window is cut proportionally. It is cut proportionally, right? When it is cut proportionally, you won't be losing a lot of throughput and you won't be losing packets. Right? So this is essentially how a TCP's behavior looks like. So, I mean, if you want more details about it, you can take a look at the previous video. But I'm just giving a recap. So we have an increase in the number of packets being sent at every congestion window, right? At every window. And at one point, when it experiences packet loss, it completely drops to 1 by half of what it was. Half of what it was. So once again, it increases and then it decreases. So this creates something called sawtooth diagram. It's like a sawtooth. Right? So ideally, if you look at it, if this is the maximum capacity of the link, then TCP should be able to TCP, if it keeps sending exactly at this level at every time instance, then it's perfect. But how do you discover this? How do you know if this is the capacity of the link? Because the capacity is highly dynamic. It depends upon the other traffic in the link, and you cannot determine in advance just based on the link capacity. The link capacity may be 1 MB or 1 Gbps, but because of other traffic, the capacity actually drops. Then, based on capacity, you give the input TCP saying you can send this much, then that's going to fail every single time. So that's the dynamic challenge. Everything here is very dynamic. Right? So this is the usual TCP. Vanilla TCP or TCP red. So this is TCP. Now this should be the ideal way in which the graph works. You start sending, and then you send packets, constant rate, right? And that rate should be just below the maximum capacity, but this is not. So the point that DCTCP tends to uh, work on, or rather leverage on, is to reduce the congestion window, reduce the sending of packets. When I say reducing the congestion window, it might usually be confusing for people who are new to this area. So when somebody says reducing the congestion window, that means you're reducing the rate of packet being sent. Why? Because congestion window is nothing but the amount of packets being sent in a crude way. Keep it like this. Why? Because every time congestion window has a value. If the value is 3, then TCP will send 3 packets and then wait for the response and then send. So in congestion window is 12, TCP will send 12 packets one after the other, back to back. So that's basically the behavior of TCP itself. This is how multiple disjoint nodes um, communicate and send packets between each other. And then this is basically an example of the data center architecture where you have all these worker nodes, and these worker nodes send traffic at the same time. That means this switch has a queue, buffer is filled up. Because the buffer is filled up, you get packet drops and huge delays. So the idea here is to let this is the sender, this is the receiver, this is the sender, this is the receiver. Then even when the buffer is this much full, let's say 70% full, you let the sender know that the buffer is getting full, so you reduce the rate at which you send packets. That's it. You're just going to reduce the rate at which you're sending packets. That's all. So to do that, they take the help of something called ECN, explicit congestion notification. So ECN, what it does, it marks packets, and these packets are marked in the onward direction. Once it reaches here, in the backward direction, it is conveyed to the sender. Thereby, it reduces. And how is the sender rate reduced? It is by cutting down the congestion. So now that this is basically how DCTCP works in a very crude way. Details are there in the previous video. So then all this is just saying that, and DCTCP came out of a landmark paper that appeared in SIGCOMM 2010. People from Microsoft Research and Stanford University, they came together to. So this is basically an example of industry academia collaboration, right? So that's when the magic happens. So in a way, in a nutshell, it reacts to congestion before the congestion actually happens, or the packet loss, right? So this is explanation about ECN. Probably you'll find this in the video as well. So ECN generally marks packets and lets the sender know that something is going on wrong. But normal ECN, what happens? Out of 100 packets being sent, even if one of the packet is marked, this is marked, then even if one packet is marked, then the sender cuts the rate by half because they know that okay, something is going wrong. Let me avoid it. Let me cut the rate by half. But TCP does not do half. It has a formula, and this formula. So yeah, so you can always say DCTCP is equal to ECN plus the reduced congestion window. That's pretty much what it is. And this is a formula, and you reduce the congestion window at a rate that is proportional to 1 minus alpha by 2, where alpha is the fraction of packets that are marked with the last window. And then based on this, we have this question where Here the following statements are correct about data center TCP. And, right, this is what is wrong. I don't want to go through that because we already seen it before the last class. And what is the role of the alpha parameter? Yeah, it determines the fraction of packets to Marcus congestion. It's basically the formula which determines by how much you're going to cut the congestion window. That's it. So this is the story about TCP. Now moving on to computing model. Okay, so this one image from the lectures, which pretty much explains uh, infrastructure as a service, platform as a service, software as a service, and serverless computing in a very compact. Right? If you take a further look at this diagram, this one. So if you take a look at this diagram, you can see that there are 1, 2, 3, 4, 5 tires. Right? The first is on-premise. So the example that I gave you was imagine you have a computer and you want to create your own website, which is this HTML website, and you want people to address it. Or let's say you are building HTML website for NPTEL forums. So what would you do? You create your own content using HTML. You'll have a database also, and then you'll have a backend processing language, which will work perfectly well in that computer. But is this good enough? Is this enough? The answer is no. Why? Because this is monolithic. Monolithic means everything at the same place. So when will this problem? When will this manifest? When will this problem be manifested? Let's assume the NPTEL forum is coded very well, and every day thousands of people are accessing the NPTEL forum. So what happens when a lot of people access the forums or other whatever you've created? Your system gets overloaded. So when the system gets overloaded, um, it's pretty much a game over. So you'll need to scale it. Scale the system. So what will you do? You'll probably create one more. You'll buy one more machine, and you will put a copy of this. Or how will you manage the database in two different places? Right? So all of these things are there. So with this monolithic architecture, you cannot scale things that easily. It's very, very difficult. Which is why people went towards something called infrastructure as a service. So here you create your own applications. You have your own data source, you have your own middleware, your own runtime, your own operating system, and you build it on top of someone else's hardware. And you're paying a particular subscription fee because they are maintaining the hardware and they are able to give it to you for a very low fee also. And that's because they're doing it at scale. They're doing it at large scale. Some examples for this are also, I think, places like Red Hat. I forgot the name. Probably Hostinger, all these. GoDaddy, they also allow you to host your own website on their hardware. Right. Okay. This is I when talking about the service is where you take away this OS also. You don't care what OS they're running. You're just going to write your own code and you're going to push it. That needs to work. I don't care whether they're using Linux or they're using Windows or whether they're using something else. It doesn't matter. And then when it comes to serverless, the difference, the jump here between this and serverless is in serverless, you're not even going to write your own code. No, even your own code. And that is, it's funny, you can ask, how can you do something about writing your own code? That's because they've already written all the code and they've given it exposed to you in the form of functions, some constant functions, and you just need to call it. And in my case, the example I showed in the last class was a IoT application where we used a database. Uh, we don't call it database in their terms, but we basically invoke the database on particular sensors input. Take a look at the previous video. You want to see that there, right? And then this is basically serverless, where you just call the functions, all the functions, and the meaning of serverless has its own connotations, has its own interpretations by multiple people. So you might find different meaning everywhere. Right? And finally, software as a service is very restricted. You only use the software that somebody else has built, but it's on the cloud and you can access it using your browser. So that is software as a service. So right. So now let's take a look at the questions. So once again, let me transfer the questions. Yeah, right. I'm just waiting for the last question to appear. Okay, good. So we'll directly jump into the questions because if we do the theory ones and then go to the questions, it's gonna be tough. So okay. Which of the following statements are correct about computing models? So in the platform as a service model, PES, the user manages services such as runtime, middleware, and operating system. If we just go upstairs here, we pass right runtime, time, middleware, and operating system. These are not managed by the user. Only the ones that are in blue color are managed by the user. So that is correct also because in the platform as a service, you ask your provider to give you a platform on which you can do your own drawings, or in this case, drawings with your own program that you want to run on top of the platform that are given to you. Okay, so, is this correct? It is not correct. Secondly, in the platform as a service model, the cloud service provider. Cloud service provider is whom? He's the person who is giving you the service, who has so basically you're the customer of the cloud service provider, right? And he manages CSP manages the services runtime, middleware and operating system. This is true because he's managing. And in this question, if they also add on server storage networking, add on servers, storage, networking, okay, add on these also, then the statement still holds true. So in infrastructure service model, this is IaaS. The cloud service provider manages services such as runtime, middleware, and operating system. This is true. People in IaaS, right? They are saying runtime, middleware, and operating system. So runtime, middleware, and operating system are not managed by the cloud service provider. They're managed by the user who wants to use it. Basically, you who wants to do something, right? So this statement is false. So next is in serverless computing model. The provider manages the underlying infrastructure, right? Even without looking at it, we can say it's true because this is also very similar to PaaS, where everything underlying below it is managed by the cloud provider, right? So the answers are B and D. Right. So what is this disadvantage of what is the disadvantage of a monolithic architecture? So we looked at what this monolithic architecture is. It says in a single system with having your front end, uh, database, and your back end all in the same system in a monolithic architecture, right? Where you don't have any clear separation of these, the sense that you can't scale just the database outside this. Right? This is basically a monolithic architecture. So what are all the disadvantages of it? So is it easier to deploy and manage? Yes, it is. It is definitely easier to deploy and manage, right? Because it's all in the same system for you. There's no separation, so it definitely easier for you to deploy. You write your code and then you just say it's done. Now I'll put it on the internet. Right? That's basically what this is. So yes, it is easier to deploy and manage. Secondly, uh, it is easy to debug. Very well, yes, because all these are in the same components and not separately in different. Not like this. The database is not split, so you know where the fault occurs, and you can pinpoint it in a lot more easier fashion. Right? So it is also yes, it is not a disadvantage; it's an advantage. It is less scalable than other architectures. Yes, this is actually a disadvantage. Actually, disadvantage. This is a disadvantage. So therefore, this is the answer to this question. Right? And it is more scalable. No, it is not more scalable. So basically, this is an advantage. This is an advantage. The statement is false, and this is a problem with monolithic architecture. So which of the following statements is incorrect about microservices architecture? So what is this microservices? Let's have a short look at it. Okay. So we've been looking at monolithic, right? Monolithic is when you're front. Okay. So let's first define how an application. Okay. Let's say you're building a web app. So what are all the components of the application? What are all the components? You have a front end. So this front end could be either simple HTML or it could be a JavaScript framework like React, Angular, etc. So this is something that the developers will know is the front end. So the front end is basically decoupled from the back end, and the back end is basically going to have another language that communicates with the front end, the back end. The back end could be something like PHP or even Node.js, etc. Now this backend also communicates with the database. Backend also communicates with the database. Okay. All right. So previously we built all of this and we put it into the same system, and that's why it became monolithic. But now you'll be coding the front end, right? And you'll be putting this front end into a system. This is computer one, let's say server one, and you're putting this back end into another system. This is server two, right? And this all these servers have an IP address. The front end, let's say IP address is 1.1.1.1. IP address 1.1.1.2. And then the database also, I'm putting it in a separate system. 1.1.1.3. Correct. So, by the way, the databases could be anything. It could be SQL or uh, MongoDB, Postgres, PostgreSQL, etc. Okay. So this is how it is. And okay, now that you see a HTML web page on your browser screen, and you click a button, so what happens? It sends some data, and then it receives it. And how do they communicate? The recent paradigm I'm talking about is called JSON. JSON format. You must have heard of JSON. No problem. You can take a look at it. So you send some JSON, and based on the JSON, this backend processes that JSON, and if it needs an access to a database, it goes to the database, it fetches the value, and then it gives it back to you. Okay, so that's how things function. And this JSON is basically uh, given by calling something called APIs, right? That is exposed by the back. They expose APIs, and APIs are nothing but URLs. Okay. Okay. This much is enough to understand microservices, right? Yeah, I'll just be back in 2 minutes. Just stay tight. You can take a look at this and if you have any questions you can ask me. I'll be back in 2 minutes, right? Sorry for that. So have setup ready, right? Now, in a non-monolithic architecture, you will probably be scaling. Right? So you have a front end now, so have a back end, and you will be having multiple instances of the database. Why is that? The fault tolerance as well as load balancing, right? If many people are accessing it, then you can probably just the backend will load balance and will send it to the database instance that is basically multiple instances. So these are multiple instances of the database and the front end, of course. Right? So now this is with respect to how the uh, uh, physical aspects of the applications are organized. Right now, when we talk about microservices, we're talking about small services. Okay, we say small services. Now we're talking about logically self-sufficient services. So for this, I'll have to uh, split, uh, slightly change the example. So imagine if this is your NPTEL forums. So the forum is basically going to have a login system, right? And it is also going to have a place where you can post messages and read messages, right? A login system, now the system. So, so you have these two logically separate functionalities. Right? Separate functionalities. Okay. So with these logically separate functionality, you can either store the data that is required for login system in all of it, in all the instances, and the message data also on all the instances. This is what is happening in the usual case. Or you could do something else. You could probably club two of these. Both. So this one maps to the login system, and this will have data only to the message read and write services. So what you're doing here is you're creating a logical partition based on the business project. Based on the business. So essentially what will happen, the front end is calling some API. Right? This goes to something called as an API gate. So an API gateway is nothing but you see the URL, then you find out which system this call belongs to. Either is it for the login system or is it for the message read and write system? So depending upon that, the request is going to be directed either to the login system or the message read and write system. So now we can say this whole aspect is one microservice. and this, right, is another microservice. So, in a nutshell, every application has its own business logic. When we say business logic, it means it is the logic that is specific to that application. If you take a shopping site, you will have a shopping site. You will probably be having cart, right, and then purchase, and then login system, right? So all of these are basically disjoint, with respect to uh, the business logic. And the business logic is what I mean. But there are instances where things have to be updated across all of these microservices. Right? There has to be updations across. So these are all things that happen. But generally, the design of a microservice is in such a way that you avoid multiple updates across microservices. You avoid these multiple updates across microservices. Right? So I think with this introduction, let's just answer this question. Right, the question is over here. So, which of the following statement is incorrect about microservices architecture? Individual components should be loosely coupled, allowing for greater flexibility and scalability. You see, which of the following is incorrect about the microservice architecture? So, it definitely does loosely coupled. And when I was saying that they are separate components, they are loosely coupled components, meaning they are coupled, basically coupled, but they are loosely coupled. So it is true. So therefore, it gives a lot of flexibility, and you can scale things individually as well. You can only scale this. You can create 10 more instances of this particular aspect if on a particular day you are expecting more number of people to that particular operation. So you have this flexibility. So this statement is true. True. Second, individual components should be tightly coupled to maximize performance. So they are saying that individual components should be tightly coupled to maximize performance. No, this is basically the converse of the statement. This is false. Right? Failure of one component does not impact overall service. True. It's called fault tolerance. Meaning, even if this case the message part of it, right? If this microservice is down, you can still log in, even though you might not be able to do anything further in it. You'll be able to do other services. It's not like the whole thing goes down. Right? This is advantage, and that's true. And there's a lower risk for building and upgrading the components. Yeah, you can upgrade individually. Sometimes, usually, what happens in production systems, we call these as production systems. So, when systems are running right now, people are live. They're using these sites, Flipkart, call every second. You have someone or the other who is performing some action in it. So, you cannot just walk inside the data center and upgrade hardware or upgrade a particular piece of software. So you need multiple instances of it running so that you can upgrade one instance and then that is migrated across multiple other instances. So all of these complexities are reduced with respect to microservices because they are all separate components. and therefore there is less. So therefore we have to do specials. Right. 6. Which of the following statements about network processors is not primarily true? This is just a direct question from your classroom. So, does it mean that a processor specifically designed for networking applications? It is not primarily true. In the sense, you're looking for a false statement. So yeah, so this is true because it's a okay. So I think I was not touching, but these are all specific processors that excel in one aspect of computation. This aspect is network operations. For example, they might have accelerators. For example, if you want to do any cryptographic functionalities, then um, you'll need an accelerator, meaning the processor should be fast in doing that one particular operation. So it is not a general purpose processor, it is a specific processor, right? And that's why they're specifically designed for networking applications. So that is true. So special memory controllers for moving packet data. Yes, true. Uh, See, when we talk about networks, we talk about packets. The packets are inbound switches, and these switches have these network processors which specialize in the process of taking this packet and putting it on the output link as soon as possible. Right? So we need to do these things as soon as possible so that you have very less network latency. And that's why these network processors are specifically built for this particular use case for network. So this is also primarily true. But a hardware device that encrypts and decrypts network traffic. Although I told you about encryption and decryption using accelerators, that is not a primary function. Right? Although in today's context, if you take a look at it, it is very much necessary and important, but we've still not reached that part. That's it. So consider this as false for now. But it is network processors are also supposed to uh, uh, support cryptographic operations like this one. It's not, and also this is not a hardware device, right? So probably that's why this is false. Yeah, keep it like that. And the high-speed packet processing. So of course, it should have a high-speed packet processing. So also true, true, true. So the answer is this. C. So which of the following statements are correct about software architectures? So microservices architecture more scalable than monolithic architecture. Yes, this is true. We don't even have to think 1 second about this. This is true. Serverless architecture provides complete control over the underlying infrastructure. Absolutely not. You don't have any control. You only have, in fact, you can only call some functions from your provider. That's all. Some API. That's all you can do. Nothing more than that. So this is false. And then you have serverless architecture has limited control over the underlying infrastructure. Uh, has limited control over the underlying infrastructure. Yeah, this is true. Basically, this is the converse of this. This is true. You have limited control. In fact, that no control at all, other than scaling. you say you want 10 instances, they'll give you 10 instances, or not even that much. When it comes to serverless computing, you won't even know it's running on servers. You won't even know how much of the server capability is being given to you. Just that whatever lambda function, whatever it is that you've called, it will run. No one's gonna tell you how much underlying hardware is being used and all of that. You don't know worried about that. They'll run it. They'll meet your expectations. That's it. AWS Lambda is what I gave an example for in the last class. Then take a look at that video where we used AWS Lambda to build an IoT sensor system where the system automatically sends alerts to a mobile phone. And so this is something that we had explored. And then now there is Google Cloud also. Google Cloud is also there. And Microsoft Azure is also, of course, the Azure and Lambda have been there for a long time, and Google Cloud is also here. So these are all serverless platforms. Very true. Okay, so that's just A, B. Oh, I'm sorry. It's true. Okay. This is a question that dwells a little bit into the serverless architecture. So when it comes to the serverless architecture, there is something called message delivery. This is a very small niche, but anyway, let's take a look at it. Right. So there are three different semantics. Okay. First one is at most once. Second is at least once. And the third is exactly. Right. So this is basically with respect to multiple nodes in the serverless architecture communicating with each other, and in terms of sender receiver paradigm. So when you say at most once, right? This approach, what happens is when they send a message, when the sender sends a message to the receiver, uh, it just sends it only once. It doesn't know. It doesn't matter whether the message sends the receiver or not. It doesn't care. So it is just once. So basically, this is nothing but the best effort approach. Um, Next is you have the at least once. Comes to at least once. So you send it once, and it basically guarantees that if in case message is dropped in between or because of any anomalies could not be delivered, then the message will be sent again, and it will be sent again and again and again till it reaches, right? Message delivery guarantee. Finally, exactly once. It's a very confident paradigm. where you will send the message only once and delivery is so these are all the three different paradigms in nutshell. So let's look at it. So the at least one, number two. So the at least once semantics can result in duplicate messages being delivered, right? Yes, messages delivered guaranteed, but how by sending multiple messages? So if in case there are situations where due to latency or due to other issues, other anomalies, the message can be repeated once more until reach the locator, reach the receiver. So therefore, duplicate messages are possible. So yeah, yes, this is true. Okay. Second, exactly once message delivery semantics, it ensures that message cannot be lost or duplicated. Yes. Uh, this is because exactly once means I sent it once and ensures that message is not lost and it will be sent. So this is through a lot of coordination. It's like an exclusive path between the sender and the receiver, and you have guarantees. This is also true. By the way, this is number three talking about. And at most once, message delivery semantics provide no guarantee that a given message will be delivered. At most once, at most once is what that's number one I talked about. Provides no guarantee that a message will be delivered. Yes, it's also true. If you just send it once and then you're like, I don't care what happens. Whether the message reach the person or it does not reach the person, it doesn't matter. So this is also true. Exactly once message delivery semantics is often used if there are some duplicates or lost. There is a tolerable no. This is only used when you need absolute perfection, where you cannot tolerate duplicate messages or you cannot tolerate lost messages. Okay? So this is false. The opposite of the statement is true. The answer is so. Finally, we're coming towards something called in-band network telemetry. INT as they call it. Okay, so what is this INT? So INT is a network monitoring framework for collecting and reporting network status. Right. So I'll give you the answers and then we'll talk about the what INT is. Answer is yes. This is true. Reasons. Okay. This is true. And P4 with in-network and by-network telemetry can find how long the packet queued at each stage. This is also true. Now, what is this P4? Probably you might have forgotten, but I'll give you a refresher right now. That's what we're going to look right after this. And in-network telemetry is a framework that is used to encrypt network traffic. No, it's false. It's not a framework used to encrypt network traffic. That has nothing to do with in-band network. Int uses PISA framework, so it's a protocol independent, which architecture for telemetry data collection and transport. Yes, this is also true, right? So the answer is these things. Now let's have a brief look at what int is. Probably we don't have time, so I'll skip a little bit and then we'll move towards data programming and I'll show you how an example program of P4 runs. So int is, so what is network telemetry? So basically you have switches in a data center, let's say, and so it's a data center. Right? The data centers. And you basically have packets that are coming here, and some packets go here, some packets go here, 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 here. So all these switches are having some packets that are coming in, right? And of course, in the end, it goes to some worker nodes, and the reply comes back. But for the data center to provision its network and to gauge or to understand how the data center is performing, they need some data packets. The network administrators need data about the packets and the flows, right? So because they need data about the packets and the flows, how will they get it? They'll know, okay, in this switch, 10 packets came, and 5 packets were sent in this direction, 4 packets in this direction, 6 packets in this. But in this switch, what came inside was only 5 packets, which means there's a packet loss. Right? So in a way, if you verify this data about the way the flows go inside a data center, then you can identify faults, you can identify black holes, you can identify a lot of scenarios which you might want to avoid. So this data, right? So this is called telemetry data. So all the telemetry is collected at one location. This is one paradigm. All the telemetry is collected here itself, and it is exported to the client. So there are some papers with respect to this kind of an architecture. One is flow radar and loss radar. Right? These two papers basically they use P4, but not to see how much time did a packet spend in the queue at a switch. Probably this is also another telemetry data which will help you determine how the network is performing. With the help of telemetry data, you can tune your network to behave or to improve its performance. Right. So this uses paradigm of P4 as a language, right? And it's language to what? Language to program data planes. Okay. So the language to program data planes. What are these data planes? I believe you would have studied this, but now we'll take a look at P4 and how do you program a data plane. And by data plane, in this case, we're using a switch, not just any switch, it's a programmable switch. Right? It's a programmable switch. Okay. So I'll show you one example of P4 and how you can write your own P4 program and how you can program your switch. So I'll close this share and then I'll open it. Just give me 1 minute. Just finding out if you're able to see. Okay, now this should right. So this is basically the official repository of P4, where we are going to write a simple basic forwarding. All right. So I'll just give you a moment to read through this text, and I'll be back in 2 minutes. Yeah. So, you have a topology where you have two, three, four switches. Switch one, two, switch three, and switch four. And mind you, all of these switches are P4 compatible. Hence that this exercise, what it's going to do is you're going to write a program that implements basic forwarding. So this basic forwarding is nothing but if a packet comes in port number 1, it's going to send it to port number 2. Or if it comes to port number 4, it will send it to port number 1, something like that. So in this case, you're going to install rules or write a program onto the switch S1 in such a way that any packet that comes from H1 hit this port number 1 and we'll forward it on to port number 2. Right? So that's pretty much what we're going to do. This is basic forwarding. And to keep it simple, we will just implement forwarding for IPv4. We have IPv4 based forwarding. So with IPv4 based forwarding, the switch must perform following actions for every packet. So every packet that hits the port number 1, it needs to do first, it needs to update the source and the destination MAC addresses. And second, it needs to decrement the time to live in the IP header. TTL field. I believe we spoke about this long time ago in one uh, class. Spoke about it in the context of header fields and why header fields are important. And then finally, it needs to forward the packet out through the appropriate port. So the switch, it has a single table. So basically, if you know network programs, network devices, they use tables, mostly multi-action table. But yeah, in this case, it's multi-action table. So the control plane will populate static, right? So there's a table, and you are going to populate that with rules. And what do these rules look like? Rules are like, if this is the destination IP address, then send it out to port 2. Or if the destination IP address is 10.0.1.1, then forward it to port 1. Right. So, right. So it's the control plane will populate with static rules. And each rule will map an IP address to the MAC address and output port for the next call. So we have already defined the control plane rules. So you only need to implement the data plane logic of your P4. Right. So we will use the following topology for the exercise. It's a pod of a fat tree topology. I think we studied this fat tree topology also. So this is a single pod of this fat tree topology, and therefore it's referred to as a pod topology. Actually, one. Okay, and they've also given beautiful steps here for you to get started with P4. You have step 1, which is you need to run the code. Let's do exactly what they've said. I'm not going to do anything beyond that. Just to make sure I'm not confusing. Sorry. And by the way, this is a Linux-based system. So this is basically what we call a terminal. Terminal is nothing but the equivalent of a command prompt in Windows. And I'm very sure most of you should be familiar with this. If you look at this folder, on this folder, we have this P4 program called basic. Right? So this is a very basic P4 program. So you have many sections in the P4 program, though you might not understand everything at this point of time. I just wanted to bring in some practical aspects to what you learned theoretically in this course. You learned about P4, you learned about data programming. So it is only right if you see how this P4 is or what this P4 is instead of it remaining a mystery. Because just this year, P4 was added to Google Summer of Code, which means it's becoming a mainstream language. So probably there are good opportunities ahead if you want to specialize in network programmability, right? So so if you correct, so this is one direction you can take in your career path if you are interested in advanced networks or computer networks. Right? So you're defining some header fields. What are these header fields? You know all these header fields, right? Ethernet. What does Ethernet have? Destination address, source address, and then you have IPv4. IPv4 has which are all the header fields that it has. It has version. Now this is header length, differential services, total length, identification fields, flags, fragmentation offset, TTL, protocol, checksum, and then finally you have the source address and the destination. So the source address, IP address underscore T, is nothing but a 32-bit variable. So I'm type defining this as IPv4 address, and I'm declaring a variable called source address and destination address. So far simple, right? And then finally, inside a structure called headers, I am declaring Ethernet and IP. That's it. Now, why are we doing this? We're doing this because whenever a packet is coming to the switch, you need to be able to parse the header fields and keep it in your hands. So when you parse the header fields and you keep it in your hands, you have a place to store them. And that is where we have these variables, right? Probably I'll try to increase the size. All right, I'm not able to find how to increase the size. That's fine. Okay. I hope you can read what's there on the screen. Um, okay, sorry. Okay. So now you've defined all the header fields, right? So the program is similar to a C or C++ program, but it's got a slightly different paradigm. You've got header, and then you've got a parser, right? So this parser, this is what we have to write this part of the code. Um, so what I'll do is, so the same program, but the solution is filled up. So this is got a parser. So it starts always with the start state, and it transitions into the parse Ethernet state. You parse underscore Ethernet. So the state, so whatever state we see in transition, we will be defining that state in the next uh, as the next state. Basically. So in this state, what happens? Packet dot extract header dot Ethernet. So this header will basically contain the corresponding header fields that we have defined here, right? So here we have packet dot extract header dot Ethernet. So when you extract the Ethernet field, you're going to get all of these in your hands. You have destination address, source address, and Ethernet type. So now that is in your hands right now. So with that in your hands, you are also going to transition based on one of those particular types, which is Ethernet type. So this Ethernet type is one header field inside the Ethernet header. So if the Ethernet type basically could mean it could say multiple types. You have multiple types of Ethernet, multiple protocols that are coming on top of Ethernet. One of them is IPv4. So if it is type IPv4, then you go into this particular parse state. So if it is type IPv4, then you go into this parsing of IPv4. If it is not IPv4, it's IPv6, then uh, I'm just going to accept it as it is, and I'm going to not do anything with it. Essentially, this parser is written in order to extract the details of the packet and keep it in your hands. And um, right, so packet.extract, and then you go into parse IPv4. You have packet.extract header.ipv4, and whatever it is extracted and it is put into all of these. Right? So you have all these. So this is the parser. This is the parser part of IPv4. So, so we have done it till the parser. And now comes checksum verification. Ignore it for now. So now comes uh, the ingress processing, which is basically the processing that happens when the packet comes to the ingress of the switch. Right. So here you have two types of definitions. One is action, and the other one is table. So we spoke about tables. These are all match action tables. So these tables, they contain certain keys based on which you need to match. Without going into multiple further details, I would like to explain that these tables are just standalone uh, areas or data structures which is matched with the incoming packet. For example, if incoming packet's destination IP address is equal to any entry found in this table called IPv4 LPM, correct? And the way it's matched is with the longest prefix match. You must be aware of longest prefix match. Then what you do, you call an action that you defined above. So based on what are you calling the action? Let's take it. Right. So these are all the table entries. Okay, these are all the table entries. Um, so if you look at the table entries, so you're filling these table entries. So what are table entries is my ingress dot. So the table's name is my ingress IPv4, right? And then you're going to say this is forget about this. Leave it. So next, so this is basically what it is. So my ingress IPv4 will be matching it with header IPv4 destination address, which is 10.0.1.1, and it's a 32-bit LPM, which is basically a complete match. And the action that needs to be called is IPv4 underscore forward. So where did we see this IPv4 underscore forward? We saw IPv4 underscore forward over here. Basically, what it says is if I see this destination address, correct, in the packet, then I'll be calling an action called IPv4 underscore forward. And what is this action going to do? This action basically is called over here, and it has two arguments. One is destination address, the other one is port. So these parameters are specified from this table entry itself. The destination address is this, and the port is this. So this is the destination MAC address. Essentially, what this is saying is, if at all I see that the destination address is 10.0.1.1, doesn't matter which is the input port, I'll send it to this port number one. The destination MAC address is going to be the MAC address of this host H1. That's as simple as that. Right? And then you have another entry as well. So you have, if it is 10.0.2.2, okay, then um, you're going to send it to port number 2. Agreed? Correct? Take a look. If it is 10.0.2.2, you're going to send it to port number 2. It's as agreed upon. It's clear. And how are you sending it? It's by giving certain parameters to the action that is being called. That's it. And the port number is 2. Right. So this is the second entry. And you have the third entry. Third entry is also 10.0.3.3. 3.3 is set to port number 3. So where is the 3.3? Oh, sorry. Right. Where is 3.3? 3 is over. If it is 3.3, if it has to reach this host, then it needs to be sent to port number 4. Correct? Okay. If it is 3, then it's sending it to 3 only. It goes here, and then from here it goes here. Right? Let's not confuse it. And then if it's 4.4, it is sent to 4. That's it. I think the logic is simple. 3.3, send it to 3, and if it's 4.4, right? Now, each of these switches, I can understand this might be getting a bit overwhelming, but just thought it right to explain about these things happen. So each of these switches will have rules regarding what happens if the destination address is either 1.1, 2.2, 3.3, or 4.4. If 1.1 reaches here, what please send it to 1. Okay? 1.1, if 1.1 is the destination address at switch 2, okay? Switch 2, or switch 2 is over here. Sorry, switch 2. And then you'll be sending it to port number 4. port number 4. That's 2.2, port number 3. It is 3.3, port number 1. It is 4.4, port number 2. If it is, let's verify, right? So if it is destination address is 2.2 for this switch, right? You should probably send it to again port number 3. So it goes like this for 2.2. I wonder why, but let's take it for its word. And if it's 3.3, if it is 3.3, then it is sending it to port number 1. Right. 3.3 is right over here. And if it is 4.4, it is sending it to port number 2. That's it. That's pretty much what um, this program does. Okay. And now probably we can run this program. Okay. So because it's actually an exercise, so I'll just do and then go to solution. So now, how do you run this in this program? You just type in make run. Okay. So this will build all the essential. Probably and to remove that. So this is basically the mainnet terminal that we can talk about, right? So this mainnet terminal is basically a virtualized environment where you have these 4 switches and these 4 hosts. So how do you know that? Let us say I am having X term H1. Okay. So this opens up a new terminal to a host. Now, if I see what is the IP address of it, right? You see, it is 10.1.1. Now, if I type xterm h2, right? This is the first host and the second host. We have, so this is h2 and this is h1. Right? How do you know this is h2? This is AF config. So from h1, I am going to send traffic. Okay, how do you send traffic? We ping 10.0.2.2, 10.0.2.2. So this is the one. 10.0.2.2. Have this also, and then ping. You're able to ping right now. That's because I ran the solution itself. So before running the solution, if you try to do this, you will not be able to do it because this switch is not configured to forward packets the right way. So essentially, if you look at the P4 program, right, you have this IPv4 table, then you have an IPv4 forward, and you have a drop also. Let's ignore that for now. So what this forward does, it takes the input that you're getting from the table and puts it into the egress spec. Egress spec is nothing but where the packet has to be sent on to, which is basically what you're providing from the table. And then you are copying the destination address into the source address and the new destination address to the destination address, because L2 level addresses keep on getting uh, exchanged, or rather, when it goes to a new segment in the LAN, the source address becomes the destination address, and the destination address is the new address to which it is moving towards. Right? and we have a destination address is equal to destination address of the packet, and then finally you're reducing the TTL by 1. So the time to live, right? Because the packet should not travel for more than some amount of time in the internet. So we're reducing the TTL by 1. That's it. And this is basically the checksum computation, which happens, say, automatically. You don't have to worry about it right now. And you have packet.emit, packet.emit. Emit in a sense, you reconstruct the packet with the Ethernet header as well as the IPv4 header, and this will send it onto the port which was set over here. Essentially, this is what P4 is, and what you're doing here, to bring it into context, you're programming these switches and you're controlling these switches with the help of table rules. That's what you asked for. And probably I can understand that you might not have understood much from this small demo, but I just wanted to point you towards the right direction if you want to learn more about P4 and packet processors in the data pool, and how do you program these packet processors. Right, so I'll probably stop sharing, and right, so that's it for today. I'll be around till 8 o'clock. If you have any questions, you can ask me. Else you are free to leave. Okay.
Hello. Hello.
Yeah, Kshitij, just tell me. Yeah, hi.
Yeah, sir, this Mininet, is it open source or is it freely available for Windows and Linux both, or only Linux?
So Mininet is, in my experience, I think it's available only in Linux. But yeah, I think we can make a quick search. I'll give you the answer right now. It's for Linux basically. So have you used Mininet before?
Okay. Okay.
Have you used
No, I
Mininet
have not used. I have not used.
Okay, okay. Right. Mininet for Windows, it's basically an environment, right? So an emulation environment. Uh, oh, okay. I think probably it's for a Linux flavor only.
Okay.
So if at all you want to use it in Windows, you'll have to install a VM.
Okay.
It basically works on Ubuntu or Linux.
Okay.
Because pretty much most of the development happens.
And all the tutorial or guidance regarding it, that is also available along with it when we
Oh
download.
yeah. Yes. See, Mininet, the basic Mininet tutorial, right? So if you go to this Mininet download .org, right? I'll just point you in the right direction. Second, I'm putting it on the chat.
Yeah.
So you have it over here, and probably you have sample workflow. Get started, right? So this is how get started. You have in this link. The first link is get started. So get started. We have Mininet installation, and then this is how you install Mininet. And then they tell you, oh, just give me 1 minute. I'll give you the right documentation for this. Right. So this GitHub repo will give you the introduction to Mininet, or if none of these things work for you, probably learning from videos is the best option. So Mininet tutorials, right? So if you just put in Mininet tutorial, I probably had the best experience with this. Okay, start. So I think these things can get you started.
Okay, sir.
So you're you're studying network somewhere, or what is your background? Just curious because.
I am a professor. I am teaching networks.
Oh, okay, okay.
So would like to in the for the practicals, I thought this would be interesting. So students need to. So right now I'm teaching them socket programming and those things. But I thought
Okay, okay.
practically regarding these networks, if we can include.
Right, right. Of course. I think Mininet is this is a good tool for
So,
that.
so
Yeah.
advanced networks also we are trying to introduce one subject as an elective for the final year students. So
Oh,
that's the reason I was doing this course.
right. Then this will fit perfectly because, but Mininet on by itself is flavored for SDN. So
Hmm.
by
Yeah.
default, Mininet has a controller.
Uh,
But what the flavor of Mininet that I showed right now is P4. It's basically for P4.
right.
Probably I'll give you a link for this as well, if at all you
Hmm.
require it. Um,
As a basic video I attended in the class 8 week, 9th week, it was discussed. So I need to explore it more. Basically, I've
of
got
course,
some
of course, of
insights.
course.
Now we need to explore it on our own for more
Right,
details.
right,
Right.
right. So I'll just try to give you all the details.
Yeah.
It's actually nice to hear that. Okay, you're trying to implement this learning because students will probably choose this path.
Yeah.
Learning.
So I'll just copy and paste this link somewhere where you can access
Right,
it in the
right,
Word file.
sure, sure.
Yeah.
Tutorial. Right. So this this has the link that I'm going to share right now has inbuilt tutorials, inbuilt exercises that you can use. This is for P4 though. This is for programmable data frames. But you can also use normal Mininet and tell them and implement your socket programming on the Mininet nodes also. So they can see a huge whole environment that is functioning. For example, here what to happen is we tell them to modify TCP or write a flavor of their own TCP and see how it works.
Yeah.
So the kind of exercises that. But probably if you're looking for something advanced, then this is the best place to go. Right. Right. And if you have any other further follow-up questions, I think you have our email addresses, right? So you can definitely call us there, or I'll give you
Yeah,
the
sure.
contact.
If I have any problems, I'll definitely
Yeah,
communicate.
sure,
So
sure.
once I start implementing this,
Of
then
course,
I'll
of course,
come to. Yeah.
of course. I mean, first, you need clarity by yourself, and then you.
Yeah. So now vacation is starting, so I'll get time to do these things.
Right, right, right. Yeah. Okay. Good to know. Good to know that. Right. Nice.
Okay. Thank you, sir.
All right.